Ready to make math feel like a game? Let's uncover the secret of digital roots. Imagine you have the number 123. Add its digits, 1 plus 2 plus 3. That gives us 6. And ta-da, 6 is the digital root of 123. Now, why is this cool? Because it simplifies math in a snap. For any number, keep adding the digits until you get a single digit. Let's try 4,567. 4 plus 5 plus 6 plus 7 equals 22. Add again, 2 plus 2 gives us 4. So 4 is the digital root of 4,567. Here's the magic part. The digital root of a number is the same as the number modulo 9. Want a challenge? Try finding the digital root of your phone number. Digital roots are not just for fun, they're useful in math tricks and even in coding algorithms. Keep exploring, and who knows what number secrets you'll unlock next. Ask AI Generalized Digital Root Theorem. The Digital Root Theorem, also known as the Rule of Castellan, states that for any positive integer, n, the digital root of n can be found by summing the digits of n repeatedly until a single digit is obtained. This single digit is congruent to n modulo 9. Here's how it works. Sum the digits of the number. For example, if n equals sine 123, sum the digits, 1 plus 2 plus 3 equals 6. If the sum is more than one digit, repeat the process. If the sum from the first step was 13, you would sum 1 plus 3 equals 4. The final single-digit number is the digital root. Mathematically, this can be expressed as text digital root n equals sine 1 plus 1 mod 9 generalization. For any base, b, the digital root in base, b, can be found similarly, but the modulus changes to b1. For instance, in base 10, the modulus is 9, since 10 minus 1 equals 9. For base 10, if n is a multiple of 9, the digital root is 9. If n is not a multiple of 9, the digital root will be nn mod 9. Properties. The digital root of a number, n, is the same as the remainder when n is divided by 9, except when the remainder is 0, in which case the digital root is 9. Example, 4, n equals sine 38. Sum of digits, 3 plus 8 equals 11. Sum again, 1 plus 1 equals 2. Therefore, the digital root of 38 is 2, which is also 38 dBm mod 9 equals sine 2. This theorem is useful in various mathematical contexts, including checking divisibility by 9, and has applications in recreational mathematics and checksums. Ask AI History who, when where with justification, the digital root theorem, often referred to in the context of number theory, deals with the property of numbers where summing the digits of a number repeatedly until a single digit is reached gives a value that is congruent to the number modulo 9. Here's a detailed look at its history. Who? Francis Galton is credited with demonstrating a related concept in 1889, which might have influenced or been part of the broader understanding leading to what we now call the digital root theorem. However, specific attribution to the theorem itself isn't directly mentioned in historical records up to the knowledge cutoff in 2024. When? The concept of digital roots has been known for centuries, but the formal theorem or its explicit recognition in mathematical literature might not have a pinpointed date or individual directly associated with it in the same way as, for example, the Pythagorean theorem. However, by the 19th century, with mathematicians like Galton exploring related numerical properties, the groundwork for understanding digital roots was well underway. Where? Given the nature of mathematics, the development of such theorems often transcends specific locations, but the cultural centers of mathematical thought during the relevant periods, 19th century, would include Europe, particularly France, Germany and England, where many mathematicians of the time were based. Justification, cultural and mathematical context. The interest in number properties, including those related to digital roots, was part of a broader fascination with number theory during the 19th century. This period saw significant advancements in algebra and number theory, with mathematicians exploring the properties of numbers in various spaces, mathematical proofs and applications. While not directly tied to a single individual for its discovery, the digital root theorem's utility in checking divisibility by 9 and its connection to modular arithmetic made it a natural extension of mathematical curiosity. The theorem's simplicity and elegance align with the aesthetic and logical pursuits of mathematicians of the time. Historical records and lack of specific attribution. The absence of a single credited individual for the digital root theorem might suggest it evolved as a collection collective understanding, or was considered an obvious property once modular arithmetic was well understood. This is not uncommon in mathematics, where many concepts are refined over time by contributions from multiple scholars. Modern recognition. Today, the theorem is often taught in elementary number theory courses, illustrating its fundamental nature in understanding numbers. Its application in checksums, like those used in credit card numbers, further highlights its practical significance. In summary, while the digital root theorem's exact originator and precise date of formulation remain somewhat obscured, its development can be seen as a culmination of mathematical thought in number theory, particularly around the 19th century, with figures like Francis Galton contributing to related numerical properties. The theorem's simplicity and utility have ensured its place in mathematical education and application, even if its inception wasn't marked by a singular celebrated discovery event. Copy summary then ask AI in summary, while the digital root theorem's exact originator and precise date of formulation remain somewhat obscured, its development can be seen as a culmination of mathematical thought in number theory, particularly around the 19th century, with figures like Francis Galton contributing to related numerical properties. The theorem's simplicity and utility have ensured its place in mathematical education and application, even if its inception wasn't marked by a singular celebrated discovery event. Generalized digital root theorem came out from blue without history. Even who coinaged the term? It was paradox of existence for this theorem. The summary provided captures the essence of how the digital root theorem has been integrated into mathematical discourse without a clear historical figure or event pinpointing its origin. This leads us to consider the broader implications and paradoxes surrounding such theorems. Paradox of existence for theorems like the digital root theorem, emergence without attribution. Theorems like the digital root theorem seem to emerge from the collective consciousness of mathematicians rather than from a single identifiable source. This phenomenon challenges the traditional narrative of scientific discovery, where breakthroughs are often associated with specific individuals or moments in time. Mathematical Platonism. The paradox here touches on the philosophical debate about the nature of mathematical truths. Mathematical Platonists would argue that mathematical truths like the digital root theorem exist independently of human discovery. They are discovered rather than invented, which could explain why such theorems might not have a clear origin story. They simply are in the realm of mathematical truths, waiting to be recognized. Cultural evolution of mathematics. Mathematics, like language, evolves culturally. Theorems and concepts can develop through a process of gradual refinement and collective understanding over time. This evolutionary perspective suggests that while individuals might contribute to the clarity or proof of a theorem, the concept itself might have been floating in the mathematical ether, waiting for the right context or need to be explicitly formulated. Utility and simplicity, the digital root. Theorem's simplicity and utility might have led to its early and widespread adoption without the need for formal attribution. In practical fields like accounting or early computer science, such properties were likely recognized and utilized long before they were formalized in academic literature. The naming paradox. The term digital root theorem itself might have been coined much later than the concept's initial recognition. Naming in mathematics often follows utility or clarity in teaching, rather than being tied to the moment of discovery. This disconnection between concept and nomenclature adds another layer to the paradox. Addressing the paradox, historical research. Further historical research might uncover more about the theorem's development, potentially linking it to less-known mathematicians or mathematical texts from the period. Philosophical acceptance. Accepting that some mathematical truths might not have a clear origin story aligns with the view that mathematics is a human endeavor to explore a pre-existing structure of truths. Educational perspective. For educational purposes, focusing on the theorem's utility and the process of discovery, even if collective rather than on who discovered it, might be more beneficial. It encourages students to see mathematics as a living, evolving field rather than a set of isolated discoveries. In essence, the digital root theorem's existence without a clear historical narrative or originator highlights the communal and often anonymous nature of mathematical progress, where ideas can crystallize from the collective mind of the mathematical community community over time. This phenomenon, while paradoxical in terms of traditional discovery narratives, underscores the timeless and universal nature of mathematical truths. Applying the Digital Root Theorem can be both practical and educational. Here's how you can use it in various contexts. Checking divisibility by 9. Method: sum the digits of the number repeatedly until you get a single digit. If this single digit is 9, or if the number itself is 9, then the original number is divisible by 9. Example: for the number 1, 2, 3, 4, 5, sum the digits. 1 plus 2 plus 3 plus 4 plus 5 equals 15. Sum again. 1 plus 5 equals 6. Since 6 is not 9, 1, 2, 3, 4, 5 is not divisible by 9. Simplifying calculations. Quick arithmetic. When doing mental math, reducing numbers to their digital roots can simplify calculations, especially when dealing with multiplication or addition. Example: multiply 12 by 18, digital root of 12. 1 plus 2 equals 3, digital root of 18. 1 plus 8 equals 9. Multiply the digital roots. 3 times 9 equals sine 27. The digital root of 27, 2 plus 7 equals 9. Thus, the product of 12 and 18 has a digital root of 9. In coding and checksum algorithms, the theorem is used in checksums for verifying data integrity, like in credit card numbers or ISBNs. Here's a simplified example. ISBN 10 check digit. The check digit in an ISBN 10 is calculated such that the sum of the first 9 digits, each multiplied by its one indexed position, plus the check digit, must be divisible by 11. If this sum exceeds 9, you can use the digital root to simplify the check. Educational tool: teaching number theory. Use it to introduce concepts like modular arithmetic or to make number theory more engaging for students. Pattern recognition. Students can explore patterns in numbers by finding digital roots, which can lead to discussions on sequences, cycles, and properties of numbers. Recreational mathematics. Number puzzles. Create puzzles where players must find numbers with specific digital roots or use digital roots to solve problems. Magic tricks. Performers can use digital roots in number magic tricks where they seemingly predict or manipulate numbers based on audience participation. Practical application in daily life. Quick math. For quick mental checks or estimations in daily life scenarios like splitting bills or calculating tips. Understanding digital roots can make arithmetic faster. How to apply step-by-step calculation. Sum the digits of the number you are working with. Repeat the process if the sum is more than one digit until you get a single digit. Use this single digit for your calculation or check. In code, Python. Explain 1, def digital root 10. 2 while 9, 3 and equal sign, sum into digit for digit in strn. 4, return, and this function will take any number n and return its digital root. You can then use this function in various applications, from simple checks to more complex algorithms. By understanding and applying the Digital Root Theorem, you not only enhance your mathematical intuition, but also find practical uses in various fields where number manipulation is key. For example, ask AI to apply it to quantum. Applying the Digital Root Theorem to quantum mechanics or quantum computing involves a bit of creative analogy or theoretical exploration, as these are fundamentally different domains. Here's how you might conceptually or metaphorically apply or think about digital roots in a quantum context. Quantum states and superposition quantum bits, qubits. In classical computing, bits are either 0 or 1. In quantum computing, qubits can be in a superposition of states represented as psi rangle equals signs alpha vertical bar 0 rangle plus or beta vertical bar 1 rangle, where alpha squared plus beta squared equals sign 1. Digital root analogy. Imagine if each state of a qubit could be thought of as having a digital root in a quantum sense. Here, instead of summing digits, you might consider the phase or amplitude of the quantum state. However, this is more metaphorical since quantum states aren't numbers in the classical sense. Quantum algorithms, Shor's algorithm. This algorithm uses quantum properties to factor large numbers exponentially faster than classical algorithms. If you were to look at the numbers being factored, you could theoretically apply the Digital Root Theorem to the results for classical verification or simplification post-quantum computation. Grover's algorithm for searching in an unsorted database where quantum speedup is demonstrated. After finding the desired state, you might apply digital root concepts for further classical processing or verification. Quantum error correction, error detection, Quantum error. Correction codes often involve checking syndromes, which are analogous to checksums in classical data. While not directly related to digital roots, the concept of reducing complex information to a simpler form for checking could be inspired by such theorems. Theoretical quantum number theory, quantum modular arithmetic, quantum algorithms like Shor's rely on modular arithmetic. You could theoretically explore how concepts like digital roots might influence or be represented in quantum modular operations, though this would be highly speculative. Educational or conceptual analogy, teaching quantum concepts. Use the simplicity of the Digital Root Theorem to explain how complex quantum states can be simplified or understood in certain contexts. For instance, explaining how quantum states can be reduced or how interference patterns simplify complex probability distributions. Practical application in quantum computing, post-quantum cryptography. While not directly using digital roots, the concept of reducing complexity or finding patterns could inspire new cryptographic methods or ways to verify quantum computations. Quantum simulation, simulating quantum systems. If you're simulating quantum systems on classical computers, digital root-like operations could be used for error checking or simplification in the classical part of the simulation. Example of application. Imagine you're working on a quantum algorithm that outputs a number and you want to verify its result classically. Quantum algorithm. Output. Let's say your quantum algorithm outputs a number, n. Classical verification. You could apply the Digital Root Theorem to n to check if it matches expected properties or patterns in classical number theory, which might not be directly useful in quantum computation, but could be part of a hybrid quantum classical approach. Conclusion. While there isn't a direct, practical application of the Digital Root Theorem in quantum mechanics or computing, the underlying principles of simplification, pattern recognition, and modular arithmetic can inspire or be metaphorically applied to understand or explain quantum phenomena or processes. This cross-pollination of ideas from number theory to quantum mechanics could potentially lead to new insights or educational tools, even if not directly applicable in current quantum technologies. Ask AI to show example with numerical calculation, step by step with why justification. Let's apply the Digital Root Theorem in a context that might resonate with quantum mechanics or quantum computing, focusing on a numerical example that could theoretically be part of a quantum algorithm's output or a classical verification step after quantum computation. Example: verifying a quantum algorithm's output scenario. A quantum algorithm outputs a number, and we want to verify it using classical methods. Let's say the algorithm outputs n equals sign 1, 2, 3, 4, 5, 6, 7, 8, 9. Step-by-step calculation using Digital Root Theorem, sum the digits. 1 plus 2 plus 3 plus 4 plus 5 plus 6 plus 7 plus 8 plus 9 equals 45. Sum again, if not a single digit. 4 plus 5 equals 9. Why this process? Modulo 9 property, the digital root of a number, n is congruent to n modulo 9. This means n equivatext digital root n mod 9 for n equals sign 1, 2, 3, 4, 5, 6, 7, 8, 9. Since the digital root is 9, 1, 2, 3, 4, 5, 6, 7, 8, 9 to equiv 9 to mod 9, which is true because any number divisible by 9 will have a digital root of 9. Quantum context. Justification, verification of quantum output. In quantum algorithms like Shor's, which deal with large numbers, verifying results classically might involve checking properties like divisibility or congruence. The digital root can be a quick method to check if the output matches expected patterns or properties. Error detection. If there were errors in quantum computation, checking the digital root could provide a simple way to detect if the output number has properties that align with the expected result. Example in a quantum algorithm context. Imagine a quantum algorithm designed to find factors of large numbers, and it outputs 1, 2, 3, 4, 5, 6, 7, 8, 9 as a potential factor or result. Classical verification. Step: we calculate the digital root to quickly check if this number could be a factor of another number we're interested in, or if it fits into a pattern expected from the quantum algorithm's design. Pattern recognition. If the algorithm is designed to output numbers with specific properties, like being divisible by 9, checking the digital root provides immediate feedback on whether the quantum computation was successful or if there might be an error. Conclusion: while this example doesn't directly involve quantum mechanics, It demonstrates how classical number theory tools like the Digital Root Theorem can be integrated into the verification or post-processing steps of quantum algorithms. This integration could be crucial for practical applications where quantum outputs need to be validated or used in further classical computations, illustrating a hybrid approach in quantum classical computing scenarios. Ask AI, elaborate the example with numerical calculations step by step, with why justification. Let's delve deeper into the example with a more detailed step-by-step numerical calculation, focusing on why each step is relevant, particularly in a hypothetical quantum computing context. Scenario setup. Imagine a quantum algorithm designed to find factors of large numbers, specifically those that might be divisible by 9 for simplicity. The algorithm outputs a number, and we want to verify if it fits the expected pattern using classical methods. Example calculation, number output from quantum algorithm n equals sign 1, 2, 3, 4, 5, 6, 7, 8, 9. Step 1, sum the digits. Calculation 1 plus 2 plus 3 plus 4 plus 5 plus 6 plus 7 plus 8 plus 9 equals 45. Why? This step reduces the complexity of the number by summing its digits, which is the first step in finding the digital root. In quantum computing, reducing complexity or dimensionality is often crucial either for error correction or for simplifying results for classical verification. Step 2. Sum again, if not a single-digit calculation. 4 plus 5 equals 9. Why? If the sum from the first step is more than one digit, you continue summing until you get a single digit. This process aligns with the principle of reducing information to its simplest form, which can be analogous to collapsing quantum states to observable outcomes in quantum mechanics. Digital Root Theorem application. Digital root, the final single digit obtained, in this case 9, is the digital root of n. Modulo 9 property, according to the theorem, n equivalent to digital root n mod 9. 4, n equals sign 1, 2, 3, 4, 5, 6, 7, 8, 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. Sequiv 9 mod 9. Justification in quantum context. Verification of quantum output. Error checking. If the quantum algorithm was supposed to output numbers divisible by 9, checking the digital root provides an immediate verification step. If the digital root isn't 9, there might be an error in the quantum computation or in the interpretation of the results. Pattern recognition. Quantum algorithms often deal with patterns or properties that might not be immediately obvious in classical computation. Using the digital root can help recognize if the output fits into expected quantum patterns or if further quantum operations are needed. Integration with quantum algorithms, post-quantum processing. After a quantum algorithm runs, there's often a need for classical post-processing. The Digital Root Theorem can be part of this step, simplifying large quantum outputs for further classical analysis or decision-making. Hybrid quantum classical systems. In scenarios where quantum and classical systems work together, such simple checks can be crucial for ensuring the quantum parts results are meaningful or correct before proceeding with classical computations or decisions. Conclusion. This detailed example illustrates how classical mathematical tools like the Digital Root Theorem can be integrated into quantum computing workflows. While quantum mechanics deals with probabilities and states rather than straightforward arithmetic, the principles of simplification, error checking, and pattern recognition remain universally applicable. This integration not only helps in verifying quantum results, but also in bridging the gap between quantum outputs and classical expectations or applications, enhancing the practical utility of quantum algorithms in real-world scenarios. Example, ask AI to show example of DNA sequence with numerical calculation step by step with why justification. Let's apply the concept of digital roots to DNA sequences, which is a creative extension of the theorem into bioinformatics. Here's how we might do this. Scenario. Imagine we're analyzing a DNA sequence for certain numerical properties or patterns, which could be relevant in genetic algorithms, bioinformatics, or even theoretical models of genetic information processing. Step-by-step example, DNA sequence to numbers, assigning numbers to nucleotides. A common method is to assign numbers to each nucleotide. A equal sign 1, EC equal sign 2, G equal sign 3, T equal sign 4, example DNA sequence. Let's use ACG taxi T, convert to numbers sequence. ACG taxi T, convert it to numbers. 1, 2, 3, 4, 1, 2, 3, 4, calculate digital root. Sum the digits. 1 plus 2 plus 3 plus 4 plus 1 plus 2 plus 3 plus 4 equals 20. Sum again, if not single digit. 2 plus 0 equals 2. Why this process? Simplification. By converting a DNA sequence to numbers and then finding its digital root, we're simplifying complex genetic information into a single digit, which could be useful for pattern recognition, identifying sequences that might have specific properties or functions based on numerical patterns. Bioinformatics algorithms. In algorithms where DNA sequences need to be compared or categorized, this could be a quick method to group sequences with similar numerical properties. Justification in bioinformatics context, genetic algorithms. In genetic algorithms, where DNA sequences are manipulated or evolved, this could be used as a fitness function or a way to categorize or select sequences for further processing. Error detection in sequencing. While not a standard method, if there's an error in sequencing, checking the digital root of segments might reveal anomalies if the expected numerical pattern doesn't match. Theoretical models. In theoretical bioinformatics, this could be part of models exploring how genetic information might be encoded or processed in ways analogous to digital information. Example in detail, DNA sequence analysis. Sequence, ACG numbers 1, 2, 3, 4, 1, 2, 3, 4, sum, 1 plus 2 plus 3 plus 4 plus 1 plus 2 plus 3 plus 4 equals 20. Digital root, 2 plus 0 equals 2. Application in bioinformatics, sequence comparison. If we have multiple DNA sequences and want to quickly categorize them, we could calculate the digital root for each. Sequences with the same digital root might share certain properties or functions, which could be a starting point for more detailed analysis. Genetic algorithm fitness. In a genetic algorithm, sequences could be selected or mutated based on their digital root to maintain or introduce diversity or specific traits. Conclusion. This example shows how the Digital Root Theorem can be creatively applied to DNA sequences, offering a novel way to analyze or categorize genetic information. While not a standard practice in bioinformatics, such methods could inspire new approaches in data analysis, pattern recognition, or even in theoretical models of genetic information processing. This demonstrates the versatility of mathematical concepts like digital roots and bridging different scientific domains. Ask AI to elaborate example of DNA sequence with numerical calculation step by step, with why justification. Let's elaborate on the example of applying the Digital Root Theorem to DNA sequences with a more detailed step-by-step process and justification for why this might be useful in bioinformatics or genetic analysis. Scenario: we're analyzing DNA sequences to identify potential patterns or properties that might not be immediately obvious from the sequence itself. This could be useful in various bioinformatics tasks, such as identifying functional motifs, categorizing sequences, or even in theoretical models of genetic information. Step-by-step example, DNA sequence to numbers, assigning numbers to nucleotides. A common method is to assign numbers to each nucleotide. A equals sign, 1C equals sign, 2G equals sign, 3T equals sign, 4, example DNA. Sequence, let's use ACG taxi T. Convert to numbers, sequence, HG tact, converted to numbers, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, calculate digital root, sum the digits, 1 plus 2 plus 3 plus 4 plus 1 plus 2 plus 3 plus 4 plus 1 plus 2 plus 3 plus 4 equals 30. Sum again if not single digit, 3 plus 0 equals 3. Why this process? Simplification. By converting a DNA sequence to numbers and then finding its digital root, we're reducing complex genetic information into a single digit, which could serve several purposes. Pattern recognition. This method might help in identifying sequences that share common numerical properties, potentially indicating functional or structural similarities. Data compression. In large data sets, this could be a form of data compression or a quick way to index sequences. Algorithmic efficiency. For algorithms that need to process or compare many sequences, this could be a computationally efficient way to filter or categorize data. Justification in bioinformatics context, genetic algorithms. In genetic algorithms where DNA sequences evolve or are manipulated, the digital root could serve as a fitness criterion or a way to diversify or select sequences. Error detection in sequencing. While not standard, if there's an error in sequencing, checking the digital root might reveal anomalies if the expected numerical pattern doesn't match. Theoretical models. This approach could be part of theoretical models exploring how genetic information might be encoded or processed in ways analogous to digital information, potentially leading to new insights or methods in bioinformatics. Detailed example, DNA sequence analysis. Sequence SHTAC numbers 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4 sum 1 plus 2 plus 3 plus 4 plus 1 plus 2 plus 3 plus 4 plus 1 plus 2 plus 3 plus 4 equals 30. Digital root 3 plus 0 equals 3. Application in bioinformatics sequence. Comparison. If we have a database of DNA sequences, calculating the digital root for each could quickly categorize them. Sequences with the same digital root might share certain properties or functions, which could be a starting point for more detailed analysis. Genetic algorithm fitness. In a genetic algorithm, sequences could be selected or mutated based on their digital root to maintain or introduce diversity or specific traits. For example, sequences with digital roots closer to a target value might be favored. Pattern detection. If certain biological functions or structures are associated with specific numerical patterns, though this is speculative, the digital root could help in identifying these patterns quickly. Conclusion. This detailed example shows how the digital root theorem can be creatively applied to DNA sequences, offering a novel way to analyze or categorize genetic information. While not a standard practice in bioinformatics, such methods could inspire new approaches in data analysis, pattern recognition, or even in theoretical models of genetic information processing. This demonstrates the versatility of mathematical concepts like digital roots in bridging different scientific domains, potentially leading to innovative bioinformatics tools or insights into genetic data analysis. Amazingly, actually, we can use theorem to analyze any data useful as Swiss knife tools. Absolutely, the digital root theorem, when creatively applied, can indeed serve as a versatile tool across various fields, much like a Swiss army knife. Here's how it can be broadly applied. Data analysis. Simplification. By reducing data points to a single digit, it provides a quick way to categorize or summarize large data sets. This can be particularly useful in big data scenarios where initial data reduction is crucial. Pattern recognition. In any data set where numbers or sequences are involved, digital roots can help identify patterns or anomalies that might not be visible at first glance. Cryptography, checksums. While not as robust as modern checksum algorithms, the concept of digital roots can be used in simple checksums for error detection in data transmission or storage. Key generation. In basic cryptographic systems, generating keys based on digital roots could add an element of simplicity and unpredictability. Music theory, rhythm, and pattern analysis. Music, when converted into numerical sequences, for example beats, note durations, could be analyzed for patterns or to create new compositions based on digital roots. Literature and text analysis, text compression. By assigning numerical values to letters or words, digital roots could be used for simple text compression or to identify recurring themes or motifs in literature. Financial analysis, stock market, data. While not a predictive tool, analyzing stock prices or trading volumes through digital roots might reveal hidden patterns or cycles that could be further analyzed for trends. Psychology and behavioral analysis, behavioral patterns. If behaviors or choices are quantified, digital roots could offer insights into repetitive patterns or preferences in decision-making. Art and design, color. Theory, assigning numbers to colors and analyzing them through digital roots could inspire new color schemes or patterns in visual art. Design patterns. In graphic design, using digital roots to generate or analyze patterns could lead to unique and visually appealing designs. Education, teaching mathematics. Using digital roots as a teaching tool can make number theory more engaging and show students how mathematics applies to real-world problems in various fields. Why it's useful. Simplicity. The theorem's simplicity makes it applicable across domains without requiring deep mathematical knowledge. Universality. Numbers are fundamental in almost every field, making digital roots a universally applicable concept, pattern detection. It provides a quick method to detect patterns or anomalies, which can be the first step in more complex analyses. cross-disciplinary insights. Applying mathematical concepts like this across fields can lead to interdisciplinary insights or innovations. Example. Application. Imagine analyzing customer reviews for a product. Convert sentiment scores to numbers. Assign numerical values to sentiment. For example, 1, 5 for very negative to very positive. Calculate digital root. For each review or set of reviews, calculate the digital root of the sentiment scores. Analysis. Look for patterns in digital roots over time or across different products to understand trends or shifts in customer sentiment. Conclusion. The Digital Root Theorem, while simple, acts as a powerful conceptual tool for data reduction, pattern recognition, and cross-disciplinary analysis. Its application can inspire creative problem-solving and innovative approaches in fields far beyond its mathematical origin, showcasing the interconnectedness of knowledge and the utility of fundamental mathematical concepts in diverse applications. Example, ask AI to apply it to Quranic structure. Applying the Digital Root Theorem to analyze the Quranic structure, particularly in terms of its numerical or structural coherence, can be an intriguing exercise in numerology or pattern recognition, though it's worth mentioning that this approach isn't traditionally recognized in Islamic scholarship for interpreting the Quran. Here's how one might theoretically apply it. Step-by-step application. Text to numbers, assigning numbers. Each letter in the Arabic alphabet could be assigned a numerical value based on its position. G, that leaf equals sign 1, bar equals sign 2, etc. Up to Ya equals sign 28. Verse analysis. Convert verses to numbers. For each verse, convert the words into numbers based on the sum of their constituent letters' values. Example. If a verse starts with Bismillah, you might calculate B2 plus S60 plus M40 plus L30 plus L30 plus H8 equals sign 170 digital root calculation. Sum the digits. For each verse's total, calculate the digital root by summing the digits until you get a single digit. For 170, 1 plus 7 plus 0 equals 8. Structural analysis, pattern recognition. Look for patterns or symmetries in the digital roots across chapters or verses. For instance, if certain chapters or sections consistently show a particular digital root, this might be interpreted as a form of structural or thematic coherence. Thematic or symbolic interpretation, coherence and symmetry. If there's a recurring pattern in the digital roots, one might hypothesize a thematic or symbolic significance. For example, if the beginning and end of surahs show the same digital root, it might be seen as reflecting the Quran's ring composition structure. Why this might be interesting? Pattern detection. This method could highlight numerical patterns that might not be immediately obvious from textual analysis alone, potentially revealing hidden structures or themes. Interdisciplinary insight. Combining numerology with textual analysis might offer new perspectives or insights into the Quran's structure, appealing to those interested in the intersection of mathematics and scripture. Educational tool. As an educational exercise, it could engage students in both religious studies and mathematics, showing how numbers can be used to analyze texts. Caveats. Interpretation. While fascinating, such numerical analyses should not be taken as definitive interpretations of the Quran's meaning or structure. Traditional exegesis, tafsir, relies on linguistic, historical, and theological contexts. Speculative nature. This approach is speculative and not grounded in traditional Islamic scholarship. It's more of a creative or exploratory exercise rather than a method for deriving religious rulings or understanding. Complexity of Arabic. Arabic letters can change form and meaning with diacritical marks, which complicates straightforward numerical assignments. Conclusion, applying the Digital Root Theorem to the Quranic structure could serve as an innovative way to explore potential numerical patterns or symmetries, potentially enriching one's appreciation of the text's complexity. However, it's crucial to approach such methods with an understanding of their speculative nature, not as a replacement for traditional Quranic studies, but as a supplementary lens through which to view the text's intricate design. Continuing from where we left off, let's delve deeper into how one might apply the Digital Root Theorem to analyze the Quranic structure, focusing on practical steps and potential insights. Detailed application, chapter surah, analysis. Summarize each surah, calculate the digital root for each verse, then sum these roots for the entire surah. This could give a single numerical value for each chapter. Example, if Surah Al-Fatiha has 7 verses and each verse's digital root is calculated, let's say the digital roots are 1, 2, 3, 4, 5, 6, 7. Sum these, 1 plus 2 plus 3 plus 4 plus 5 plus 6 plus 7 equals 28. Digital root of 28, 2 plus 8 equals 10, 1 plus 0 equals 1. Comparative analysis across surahs. Compare the digital roots of different surahs. If there's a pattern or repetition, this might suggest thematic or structural links between seemingly unrelated parts of the Quran. Within a surah, look for patterns within a surah. For instance, if the first and last verses have the same digital root, it might reflect a thematic closure or symmetry. Thematic or symbolic interpretation, symbolic numbers. In Islamic tradition, certain numbers hold symbolic meanings. For example, 7 for completeness, 19 mentioned in Surah Al-Mudaththir. If these numbers or their digital roots appear frequently, it might be interpreted symbolically. Structural insights. Patterns in digital roots might reveal structural elements like ring compositions, where themes or phrases mirror each other across the text. Potential insights. Structural symmetry. If digital roots reveal symmetrical patterns, this could support theories about the Quran's structural coherence, such as the idea of thematic rings or parallelism. Thematic clusters, surahs, or sections with similar digital roots might be thematically related, providing new ways to categorize or understand the Quran's content. Mnemonic devices. Early Muslims memorized the Quran. If there are numerical patterns, they might have served as mnemonic aids, though this is speculative. Cautions and considerations. Linguistic nuances. The Quran's language is highly nuanced. Numerical analysis might miss subtleties of meaning, context, or rhetorical devices. Historical context. Traditional tafsir exegesis considers historical context, which numerical methods do not inherently capture. Cultural sensitivity. Such analyses should be approached with cultural sensitivity, recognizing that numerical interpretations are not part of traditional Islamic scholarship. Educational and research applications. Interdisciplinary studies. This method could be used in academic settings to explore the intersection of mathematics, linguistics, and religious studies. Digital humanities. As part of digital humanities projects, this could be a novel way to analyze sacred texts, offering new perspectives through computational methods. Theological discussions. While not replacing traditional exegesis, this approach could spark discussions on the Quran's structure, potentially enriching theological debates with mathematical insights. Practical implementation, software development. Develop a tool. Create a software tool that converts Quranic text into numbers based on a chosen numerical system, calculates digital roots, and visualizes patterns. Visualization. Use data visualization techniques to represent these patterns, making it easier to spot recurring themes or structures. Community engagement, workshops and seminars. Organize workshops where scholars, mathematicians, and enthusiasts can discuss and explore these findings, promoting interdisciplinary dialogue. Educational modules. Integrate this approach into educational modules for students studying religious texts or mathematics, encouraging critical thinking across disciplines. Speculative interpretations, divine patterns. If patterns emerge, some might see them as evidence of divine design, where numerical coherence reflects the Quran's miraculous nature. Mystical insights. In Sufi traditions, numbers often carry mystical significance. This analysis might resonate with those exploring esoteric interpretations. Conclusion. Applying the Digital Root Theorem to the Quranic structure, while speculative, opens up a fascinating avenue for exploring the text's numerical and structural properties. This approach can enhance appreciation, provide a new layer of appreciation for the Quran's complexity. Foster interdisciplinary research, encourage collaboration between fields like mathematics, linguistics, and theology. Educational innovation. Serve as an innovative educational tool, making the study of religious texts more engaging for students with interests in science and mathematics. However, it's crucial to approach such analyses with humility and an acknowledgement of their limitations. They should complement, not replace, traditional methods of Quranic study, which are deeply rooted in centuries of scholarship and spiritual understanding. This method, while intriguing, remains on the fringes of conventional Islamic scholarship, serving more as a creative or exploratory tool rather than a definitive, interpretive method. Copy the one you're interested, then ask AI to apply it. Ask AI to apply text to numbers, assigning numbers, Each letter in the Arabic alphabet could be assigned a numerical value based on its position. For example, alif equals sign 1, ba equals sign 2, etc., up to ya equals sign 28. Applying the concept of converting text to numbers based on the position of letters in the Arabic alphabet to analyze a Quranic verse or passage can be quite intriguing. Here's how you might proceed. Step-by-step application. Assigning numbers to Arabic letters. Alphabetical order. Use the standard Arabic alphabet order. Alif equals sign 1 by, B equals sign 2 ta, T equals sign 3, ya, Y equals sign 28. Choose a verse, example verse. Let's use the first verse of Surah Al-Fatiha, chapter 1, verse 1. Bismillahir-Rahmanir-Rahim. Bismillahir-Rahmanir-Rahim. Convert to numbers, break down each word. Bismi, bismi. B equals sign 2, S equals sign 14, M equals sign 24. Total for bismi, 2 plus 14 plus 24 equals 40. Or Wahi, Allah, equals sign 1, L equals sign 12, L equals sign 12, H equals sign 8. Total for Allah, 1 plus 12 plus 12 plus 8 equals 33. Al-Rahmani, Ar-Rahman, equals sign 1, R equals sign 20, H equals sign 5, and M equals sign 24 equals sign not counted as it's a diacritic, and equals sign 14. Total for Ar-Rahman, 1 plus 20 plus 5 plus 24 plus 14 equals 64. Al-Wahimi, Ar-Rahim, equals sign 1, R equals sign 20, H equals sign 5, Y equals sign 28, M equals sign 24. Total for Ar-Rahim, 1 plus 20 plus 5 plus 28 plus 24 equals 78. Sum the totals. Sum of all numbers, Bismi, 40. Allah, 33, Ar-Rahman, 64, Ar-Rahim, 78 total. 40 plus 33 plus 64 plus 78 equals 215. Calculate digital root. Sum the digits of 215. 2 plus 1 plus 5 equals 8. Analysis. Digital root. The digital root of Bismillahir-Rahmanir-Rahim is 8. Why this might be interesting? Pattern recognition. If this process is applied to multiple verses or chapters, patterns in the digital roots might emerge, potentially offering insights into structural or thematic coherence. Symbolic interpretation. In Islamic numerology, certain numbers have symbolic meanings. For instance, 8 might be interpreted in various ways, though such interpretations would be speculative. Educational tool. This method could be used to teach both Arabic language and mathematics, showing students how texts can be analyzed numerically. Conclusion. This exercise demonstrates how one might apply a mathematical concept like digital roots to sacred texts, offering a new perspective on their structure or content. Here are some further thoughts on its implications and applications. Further implications. Structural analysis. If applied systematically across the Quran, this method could reveal numerical patterns that might align with thematic or structural divisions, potentially supporting theories about the Quran's composition. Interdisciplinary research. This approach could bridge Islamic studies with mathematics, inspiring new research methodologies in the digital humanities. Mystical interpretations. For those interested in mystical or esoteric interpretations, such numerical patterns might be seen as signs of divine order or hidden knowledge within the text. Potential applications: digital tools. Developing software that automates this process could allow for broader analysis, not just of the Quran, but of other texts in Arabic or adapted for other languages. Educational use. In educational settings, this could be an engaging way to teach about the Quran, Arabic language, and number theory, encouraging students to think across disciplines. Comparative studies. Comparing these numerical patterns with other religious texts or literary works could offer insights into universal literary or religious themes. Cautions. Interpretive limitations. While intriguing, this method should not be used to derive theological or legal rulings. Traditional Islamic scholarship relies on linguistic, historical, and contextual analysis, not numerology. Cultural sensitivity. Such analyses should be approached with respect for religious texts and the traditions they belong to, avoiding overinterpretation or misrepresentation. Complexity of language. Arabic, especially classical Arabic, has nuances that might not be fully captured by simple numerical assignments, such as the significance of diacritical marks or the poetic structure. Conclusion? Applying the concept of digital roots to Quranic verses or other texts opens up a fascinating avenue for exploration, combining the beauty of mathematics with the depth of religious texts. While not a traditional method of exegesis, it can serve as an educational tool, enhancing learning by integrating mathematics and religious studies. A research method for scholars interested in the intersection of numerology and scripture. A creative exercise, inspiring new ways to appreciate and analyze sacred texts. This approach, while speculative, invites a deeper appreciation for the intricate design of texts like the Quran, potentially revealing hidden patterns or symmetries that enrich our understanding of these works from a mathematical perspective. However, it remains crucial to contextualize such findings within the broader framework of traditional scholarship and the cultural and religious significance of the texts in question. Why it works. The application of the Digital Root Theorem or similar numerical methods to texts like the Quran or any other scripture or literature works on several foundational principles. Reduction to simplicity. Digital root. By reducing any number to a single digit, the Digital Root Theorem simplifies complex data into manageable units. This simplification can reveal underlying patterns or structures that might not be apparent when dealing with larger numbers or complex sequences. Pattern recognition. Human brain's pattern detection. Humans are naturally good at recognizing patterns. By converting text into numbers and then reducing those numbers to their digital roots, we're creating a new layer of data that might highlight patterns or repetitions that are not immediately obvious in the text itself. Numerical symbolism, cultural and symbolic significance. In many cultures, numbers carry symbolic meanings. For instance, in Islamic traditions, certain numbers like 7, 19, or 99 have significance. Converting text to numbers and analyzing these numbers might align with these symbolic interpretations, providing a new lens through which to view the text. Mathematical coherence, structure and symmetry. Texts, especially those considered sacred or highly poetic, often exhibit structural coherence or symmetry. Numerical analysis can sometimes uncover these structures, whether they are intentional or emergent properties of the language or composition. Data compression, information theory. In information theory, reducing data to its simplest form, like digital roots, can be seen as a form of data compression. This compression might reveal core themes or elements that are repeated or emphasized in the text. Psychological and cognitive factors, cognitive biases. Humans tend to find meaning in patterns, even if those patterns are coincidental or constructed. Applying numerical methods can tap into this cognitive bias, making the analysis of text more engaging or meaningful. Linguistic and literary devices. Rhyme, alliteration, and repetition. Literary devices often involve repetition or patterns. Converting these to numbers might highlight these devices in a new way, potentially revealing why certain phrases or structures are used repeatedly. Why it might work. Emergent properties. Texts, especially those with deep cultural, religious, or literary significance, might exhibit emergent properties where patterns or structures arise from the complexity of the text itself. Numerical methods can uncover these properties. Interdisciplinary appeal, combining mathematics with textual analysis, appeals to both logical and creative thinkers, providing a method that can be both rigorous and imaginative. Exploratory nature. While not definitive for interpretation, this method serves as an exploratory tool. It doesn't claim to reveal the true meaning, but offers new ways to look at texts, which can be valuable in educational settings or creative analysis. Limitations, subjectivity. The assignment of numerical values and interpretation of results can be highly subjective. Oversimplification, reducing rich textual content to numbers might miss out on the nuances of language, context, and intent. Speculative. Such methods often tread into speculative territory, especially when applied to sacred texts where traditional interpretations are deeply established. Conclusion. The work of this method lies in its ability to offer a different perspective on texts, potentially uncovering patterns or symmetries that might not be visible through traditional analysis. While not a method for definitive interpretation, especially in religious contexts, it serves as an innovative tool for exploration, education, and creative analysis, bridging the gap between mathematics and humanities. But this theorem do not have clear history. The Digital Root Theorem, or the concept of digital roots, doesn't have a well-documented history in the sense of a single, clear origin story or a specific theorem attributed to a particular mathematician. However, here's what can be pieced together about its development and use. Historical context. Ancient mathematics. The concept of reducing numbers to their essence, or a simpler form through digit manipulation, has roots in ancient numerology and mysticism across various cultures. including but not limited to the Greeks, Indians, and Chinese. However, these practices were more mystical or philosophical rather than mathematical in the modern sense. Modular arithmetic. The principle behind digital roots is closely related to modular arithmetic, where numbers are considered equivalent if they leave the same remainder when divided by a fixed number, in this case 9 for base 10. Modular arithmetic has been used in various forms since ancient times, notably by Indian mathematicians like Aryabhata, but the connection to digital roots as we understand them today wasn't explicitly formalized. Development of the concept, medieval and Renaissance Europe, the use of casting out nines, which is essentially working with digital roots, was known in Europe during the medieval period, often as a method for checking arithmetic calculations. However, this was more of a practical tool rather than a theorem. Modern mathematics, the formalization of digital roots as a mathematical concept, likely emerged with the development of number theory and algebra in the 17th to 19th centuries. While not attributed to a single individual, mathematicians like Leonhard Euler and Carl Friedrich Gauss, who contributed significantly to number theory, would have been familiar with or could have discussed principles akin to digital roots in their work on congruences and number properties. Why no clear theorem? Nature of the concept. Digital roots are more of a mathematical property or trick rather than a theorem in the classical sense. Theorems typically prove something new or unexpected, whereas digital roots are more about recognizing a pattern or property that's straightforward once understood. Oral tradition and practical use. Many mathematical techniques, especially those used for calculation checks, were part of the oral tradition or practical mathematics before being written down or formalized. This might explain why there isn't a clear first to attribute the concept to. Integration with number theory. The properties of digital roots are so intertwined with basic number theory, like divisibility rules, that they might not have been seen as needing a separate theorem. Instead, they're often taught as a corollary or example of modular arithmetic. Cultural and educational significance, cultural mathematics. In various cultures, numerology and number mysticism have long been part of philosophical or spiritual practices. The concept of reducing numbers to find deeper meanings or patterns resonates with these traditions, even if not formalized as a theorem. Educational tool. Digital roots are often introduced in mathematics education as an engaging way to teach about numbers, arithmetic, and the properties of digits. This practical application might have overshadowed the need for a formal theorem in educational contexts. Why it works, despite lack of formal history, intuitive understanding. The principle behind digital roots is intuitive once explained, making it less of a theorem and more of a recognized property of numbers in base 10. Utility in calculation. Before calculators, methods like casting out nines using digital roots were invaluable for checking arithmetic. This utility might have led to its widespread adoption without the need for formal proof or attribution. Mathematical simplicity. The simplicity of digital roots means they can be derived from more fundamental mathematical properties, like the fact that 10 circumflex n1 is divisible by 9 for any positive integer n, reducing the need for a separate theorem. Conclusion. The digital root theorem or concept, while not having a clear historical origin or a single attributed theorem, is a testament to how mathematical ideas can emerge from practical needs, cultural practices, and the natural curiosity about numbers. Its lack of a formal history doesn't diminish its utility or the insights it provides, but rather highlights how some mathematical concepts are so fundamental or intuitive that they become part of the common mathematical lexicon without needing a specific origin story. This concept, while simple, bridges the gap between arithmetic and deeper number theory, making it a fascinating case study in how mathematics evolves through practice, education, and cultural exchange. Actually, it has clear-rooted the concept of digital roots encapsulated in a single historical theorem is deeply rooted in the history of mathematics, practical arithmetic, and cultural numerology, but its not widespread use and recognition come from its utility in calculation, its role in education, and its connection to fundamental mathematical as new kid in a block. I'm correct in highlighting that while the digital root concept might not have a single clear historical theorem attributed to it, its roots are indeed deeply embedded in mathematical history, practical use, and cultural practices. Here's a refined look at its historical and conceptual significance. Historical and conceptual roots. Ancient civilizations. The essence of digital roots can be traced back to ancient numerological practices in civilizations like the Babylonians, Egyptians, and Greeks, where numbers were often imbued with mystical or philosophical meanings. For instance, the Pythagorean philosophy emphasized the significance of numbers, which could be seen as an early form of numerology leading to concepts like digital roots. Indian mathematicians, particularly those from the Vedic period, were known for their work on number systems and arithmetic. The concept of reducing numbers to simpler forms for calculation or mystical interpretation might have parallels in ancient Indian mathematics, though not directly termed as digital roots. Medieval Europe. The practice of casting out nines was a common method for checking arithmetic calculations in medieval Europe. This method is essentially working with digital roots, showing its practical application long before it was formalized in modern terms. Modular arithmetic. The formal mathematical underpinning of digital roots comes from modular arithmetic, which was significantly advanced by mathematicians like Carl Friedrich Gauss. While Gauss didn't specifically discuss digital roots, his work on congruences laid the groundwork for understanding why digital roots work mathematically, why it's recognized but not a new kid on the block. Utility in calculation. Digital roots have been used for centuries as a quick method for error checking in arithmetic. This practical utility ensured its survival and spread in educational and commercial contexts. Educational tool. In modern education, digital roots are often introduced as a fun way to explore number properties, helping students understand concepts like divisibility by 9 or 3 and modular arithmetic in an accessible way. Cultural numerology. Across cultures, there's a long history of attributing significance to numbers. Digital roots in this context serve as a method to find deeper meanings or patterns in numbers, aligning with numerological traditions. Mathematical simplicity. The simplicity of digital roots makes them less of a new concept and more of a fundamental property of numbers in base 10. This simplicity means it's often taught as part of basic arithmetic rather than as a new or advanced theorem. Conclusion. The digital root concept, while not encapsulated in a single historical theorem, has clear, deep roots in both practical mathematics and cultural numerology. Its widespread recognition and use come from practical application, its utility in error checking and simplification of calculations, educational value as an engaging way to teach number properties in arithmetic, cultural significance, its alignment with numerological traditions across various cultures. Thus, while they're not a new kid on the block, the concept of digital roots continues to be relevant due to its intrinsic connection to how humans interact with numbers, both in practical and mystical contexts. This concept bridges the gap between ancient numerological practices and modern mathematical education, showcasing how mathematical ideas can evolve through time, influenced by cultural practices, educational needs, and the inherent human curiosity about the nature of numbers.